I'm going to continue talking about the discount rate, now turning to declining discount rates. So let's assume for now that the government wants to do what the people want. And most people discount the future also because they are impatient. The pure rate of time preference is greater than zero. And if the people do that, then presumably their government should do the same. At the same time, in many countries, a majority of people have expressed the will to do something about climate change. And those two things seem to be at odds with each other. If you discount the future hard, then you don't care much about climate change. But if you care about climate change, then you argue you shouldn't discount the future so hard. So some people have argued that really what you should do is, for climate policy, use a low discount rate, and for other policies use a high discount rate. That is bad advice because it leads to inconsistency in public policy. And one of the things about the democracy, proper democracy, is that a government should be able to explain itself. It should be able to justify its decisions. And then having inconsistent decisions is at odds with that. You cannot explain inconsistencies in your behavior by definition, right? And that demand for consistency also holds for the discount rate. And for instance, you could consider a project in climate change. And because it's climate change, you would use a low discount rate, and you can compare it to a project in road safety, and because it's road safety it should have a higher discount rate. But really then what you're saying is that if your investment in greenhouse gas emission reduction saves a life, say in 25 years from now, then that life should count higher, count more than if through an investment in road safety you would save a life in 25 years from now. And that's a very strange position to take, because a life saved is a life saved. So you really want something that is peculiar. You want to apply the same discount rate because it's at least the same discount procedure across different public policies. You want to care about the long-term future, and you want to not care about the long-term future because you want to reflect what the will of the people who say, well, we're discounting, so why shouldn't you, government? This really seems to be an insoluble problem, but there's two ways, at least, of squaring this circle. And the starting point lies in a peculiar property of our conventional exponential or geometric discounting. And essentially, an exponential discount rate or a geometric discount rate, 1 over 1 plus r to the power t, or if you go to continuous time, e to the power minus rho t. If you use a discount rate like that, you have a very peculiar, at first sight, property. And that is that the relative distance between 2 years is independent of when those years are. So if you compare the discount factor at time t to the discount factor at time t plus delta, so you take e to the power minus rho t plus delta and you divide it by e to the power minus rho t, then the answer to that, the relative distance, is the relative price of these two periods in time, is e to the power minus rho d, minus rho delta, where the t drops out of the equation, which is very peculiar. Because essentially what conventional or exponential discounting does is it says that the difference between year 10 and year 11 is the same as the difference between the year 100 and 101, or 1000 and 1001. And that is a most peculiar thing to say. And indeed there's a lot of experimental evidence, and earlier a lot of observational evidence, which suggests that people do not think about time discounting like this at all. And the first to encounter this was Maureen Cropper, who you see here. And the empirical evidence suggests that people use a lower discount rate when they look further into the future, and exponential discounting simply doesn't do that. One way of doing this, and this goes back to Jeff Heal, who you see pictured here. Jeff Heal used to be at Sussex in the distant past, by the way. One way to do this is to think, well, it's really what matters is relative distance, and the year, or the difference between year 10 and year 11 is really not the same as the difference between the year 100 and 101, but really it's the difference between year 100 and 110, or between year 1000 and year 1100. And if that is how you think about things, then really, and that is what Hill noted, really what you should do is just stick in a log, right? That instead of having e to the power minus rho t, you have e to the power minus rho log t. And then the relative distance between times t plus delta and time t is e to the power minus rho log a1 plus delta t. And that immediately implies that the further you go into the future, the larger t, the lower your effective discount rate becomes. So this is a neat trick, and it sort of solves this conundrum. In the short run you can use relatively high discount rates, but if you move further and further out, your discount rate falls and you start caring more and more about the distant future. So this is a neat trick. The problem is that it's entirely ad hoc. There's not much reasoning here. He'll looked at the data, said that, well, people have a declining discount rate, and if I just stick in a log, then I have a declining discount rate. My effective discount rate is 1 plus my effective discount rate falls with my time horizon. There is more fundamental reasoning that would give you a similar result and is more palatable perhaps to economic theorists. And the first, not so palatable but it's easy to explain, goes back to the work of Christian Gollier, who you see pictured here. And let's suppose there's two people, one who argues that the discount rate should be 1% and one who argues that the discount rate should be 7%. And that matters, right? If the discount rate is 1%, then the value of £100 in a year from now is 990 pounds. If you use a 7% discount rate, then it's 935 pounds. If you use a 1% discount rate, then the value of £1,000 100 years into the future is 370 pounds. But if you use a 7% discount rate, then it's £1 only. And if you go 400 years into the future, then for a 1% discount rate it's 19 pounds, and for a 7% discount rate it is 0 practically. Now, this is just the power of discounting. So one person argues for a 1% discount rate, the other person argues for a 7% discount rate. So you can say, let's split the difference. And the difference between the 1% and the 7% discount rate is 6%. We split it, it's 3. So the average discount rate of these two people is 4%. and that is what you see in the second column here. What is the discount factor if you use a 4% discount rate? So that is one way of doing it, but it's not the only way to do it. Because really what enters into our welfare calculations is not the discount rate, but it's the discount factor. We multiply future welfare by 1 over 1 plus rho to the power t, not by rho. So we can also split the difference on the discount factor. And then you end up in the fifth column in this table, which is the average of the third column and the fourth column. So after 1 year you take the average of 990 and 935, which is 962. After 100 years you take the average of 370 and 1, which is 185. And after 400 years you take the average of 18 and 0, which is 9. So that is the fifth column. And then you can invert your discount factor, 1 over 1 plus r to the power t, to calculate what r corresponds to these numbers. Now what you see in year 1 is that your apparent discount rate for after year 1 is not 4%, but is 3.91%, and after 100 years it's 1.7%, and after 400 years it's 1.18%. So the apparent discount rate is falling, A, and it is approaching the lower discount rate. And Marty Weitzman, in a paper 21 years ago, showed that indeed in the very long run, if t goes to infinity, the effective discount rate goes to the lowest one, in this case 1%. The intuition here is as follows. If you're sort of splitting the difference between two people, then you should split the difference between them. And after 200 years or after 400 years, the person with a low discount rate still cares. There's still a sum of money that is relevant to this person, and she can see a substantial and a meaningful difference between 300 years from now and 400 years from now. Whereas the person with a high discount rate, 7% in this case, after 300 years it's practically zero, after 400 years it's practically zero, so there is no meaningful difference between year 300 and year 400. So if you want to split the difference between somebody who cares with a low discount rate and somebody who doesn't care, then you should essentially ignore the person who doesn't care, because he doesn't care. And you should just listen to the person who cares. And that is the intuition why in the long run the discount rate converges to the lowest discount rate. And in the early years both care. So we're somewhere in the middle, although slightly biased towards the lowest one. In the very long run we go to the lowest discount rate. So this is one justification for a declining discount rate. The problem with this justification is that it relies on comparing the utility of two people, or more people, and we are always, as economists, always wary of doing that. So an alternative way of arguing the same is to say, well, this is not two people who disagree about what the discount rate should be, but this is one person who is uncertain about what the discount rate should be and can't make up his mind whether it's 1% or 7%. And this interpretation goes back to Marty Weitzman, who you see here. And as you can see, the only thing that I've done is replace the picture and replace one word. The reasoning stays exactly as it was. Now Weizmann went a little bit further. Instead of just comparing two discount rates and calculating everything numerically, he showed that if the uncertainty about the discount rate follows a gamma distribution, then the certainty equivalent discount rate, the declining discount rate, the column to your far right, essentially follows this particular rule that you see here, that the discount rate at time t is alpha over 1 plus beta t, where alpha is the location parameter of the gamma distribution and beta is the spread parameter of that gamma distribution. The key thing here is that your discount rate is not constant, but it depends on t, and the further you go out, the greater t gets, the smaller your discount rate becomes. And essentially what you can do then for projects with a relatively short life, you can use a high discount rate, and you're consistent with all your other public policies. Whereas for problems with a long life time, with a large time horizon, climate change and nuclear waste, you can use a much lower discount rate. And these things matter. What you look at here are four estimates of the social cost of carbon, the good tax that we want to apply to our greenhouse gas emissions, and two particular declining discount rates, and then the equivalent constant discount rate. And if we follow Weizmann's suggestion and we apply the rule that you see there, that the discount rate falls with 1 plus beta t over time, then the social cost of carbon is $88 per ton of carbon. Whereas if we take alpha as a starting point at t is 0, so that is the discount rate that we use, and we keep that constant over time rather than let it fall with 1 plus beta t, then the social cost of carbon is 2.1%, $2.1 per ton of C. So that's a factor of almost 40, a little bit more than 40 difference, right? The other discount rule that you see there is the Green Book, where you also see a declining discount rate compared to the equivalent in the beginning constant discount rate, and there the difference is smaller. It's 18 versus 6.6. I put the Green Book discounting up here because this is actually the type of discounting, of declining discount rate that the UK government uses, which is not a sort of a continuous and smooth fall in the discount rate, but it's sort of a step change. And the takeaway message here is that yes, this circle that needed to be squared can actually be squared. We can come up with a discount rate that takes climate change into account, that does discount the short run pretty hard and therefore reflects the will of the people, and can actually be consistently applied across public policy.